Okay, let's dive into this. Welcome to our comprehensive, exam-focused explainer on the absolutely fascinating invisible movement of packets that literally powers our internet. If you're gearing up for your university exams on the fundamentals of networking, specifically Unit 2 covering HTTP and web communication, well, you're in exactly the right place. Today, we're taking a methodical, microscopic journey right into the application layer to see exactly how your browser talks to the rest of the world. So here's the roadmap for our explainer today. We're going to kick things off with the web and HTTP basics. Then we'll actually mathematically calculate connection response times, decode the text-based messages computers use to communicate, figure out how servers remember who you are using cookies, and finally, we'll look at how web caching and HTTP/2 speed up the entire internet. And of course, we'll wrap up with a rapid-fire exam review. Let's get started. All right, part 1, the web and HTTP basics. Consider this the initiation phase of our journey, where we look at the invisible actions your computer is performing countless times a day just to load a single page. Let's start by nailing down our absolute foundational definition. HTTP stands for HyperText Transfer Protocol. I highly recommend you write that down for your exam. It is fundamentally the web's application layer protocol, and it operates strictly on a client-server model. What does that mean? Well, in this model, your web browser, whether you're using Chrome, Firefox, or Safari, acts as the HTTP client. And the web server, which is sitting somewhere else in the world, just waits for your requests and sends objects right back in response. And this dynamic brilliantly illustrates how the whole thing flows. Think of it like a continuous conversation. You might have a PC running a browser acting as the client, alongside another machine, maybe a Linux desktop also acting as a client. They both send an HTTP request up to a centralized server, say an Apache web server. The server receives these requests, processes them, and fires an HTTP response right back. It's a continuous, highly systematic dialogue. Now, it's absolutely vital to understand that a web page is almost never just one single file. It's more like a giant puzzle. A web page consists of a base HTML file that references multiple other objects. We're talking JPEG images, audio clips, video files, stuff like that. And each of these objects is addressable by a URL, or Uniform Resource Locator. So if we look at the address http://www.someschool.edu/somedepartment/picture.gif, the www.someschool.edu part is the hostname. It tells us exactly who to talk to. The /somedepartment/picture.gif part, that's the path name, which dictates the exact folder and file the server needs to fetch for you. Moving on to part 2, connections and response time. Now we're transitioning down to the microscopic level to watch the TCP doorways open, and we'll calculate the actual mathematical cost of time in networking. You see, HTTP doesn't just magically beam data across the world. It relies on TCP, the Transmission Control Protocol, as its reliable delivery mechanism. Here is the exact step-by-step communication flow. Step 1. The client initiates a TCP connection to the server, specifically targeting port 80 to create a socket. Step 2. The server accepts this connection. Step 3. HTTP messages are exchanged between your browser and the web server. In Step 4, the TCP connection is closed. Now here is a massive exam fact you need to know. HTTP is a stateless protocol. That means the second Step 4 happens, the server completely forgets about you. It literally suffers from complete amnesia. It has no idea if you visited the site 2 seconds ago or 2 years ago. Let's put a spotlight on a vital networking concept you absolutely must memorize for your exams: RTT, or round trip time. RTT is defined precisely as the time it takes for a small packet to travel from the client all the way across the network to the server, and then all the way back to the client. It is the fundamental unit of delay in computer networking. So let's map that concept onto a timing diagram. In a non-persistent setup, that first RTT is used purely to initiate the TCP connection. It's just the introductory handshake saying, hello. The second RTT happens when the client actually requests the file, and the first few bytes of that file finally arrive back. After that, we have to account for the time it takes to transmit the entire file over the link. So the exact mathematical formula you want to highlight in your notes is non-persistent HTTP response time equals 2 RTT plus the file transmission time. Let's clearly juxtapose our two connection types here, because this is huge. When you request a homepage, the server sends the base HTML. As your browser reads that HTML, it starts discovering all the referenced objects, like JPEGs. In non-persistent HTTP, the browser has to open a brand new TCP door for every single image it finds. So if there are 10 images, that's 11 separate TCP connections. You're paying that 2 RTT penalty over and over, which creates massive operating system overhead. Persistent HTTP, on the other hand, is much smarter. It leaves the TCP connection open. Multiple discovered objects can be sent over that single connection, which effectively cuts the response time in half. It's a real game changer for speed. Okay, part 3, HTTP messages, methods, and codes. We are now going to decode the actual text language that computers use to speak to each other. Now, what's really interesting here is that an HTTP request message is written in plain ASCII text. It's totally human readable. At the very top is the request line, which contains the method, the URL, and the HTTP version. Right below that are the header lines. These are things like host, connection, user agent, which identifies your specific browser, and accept language, which tells the server if you prefer, say, English or French. Then you'll find a mandatory blank line, followed by the entity body, which is used if you're actually sending data to the server. That request line relies on specific HTTP methods to give the server instructions. Let's connect these highly technical methods to everyday actions. GET is what your browser uses to retrieve data. It is the absolute backbone of normal web browsing. POST is used when you are sending user input up to the server, like submitting a login form or signing up for a new account. Head is exactly like GET, but it asks the server to only send the headers, not the actual file. It's a great diagnostic tool. PUT is used when you want to upload or replace a completely new file on the server. And delete, well, that one's pretty self-explanatory. It removes a resource. Once the server processes your request, it replies with an HTTP response message. And the structure is remarkably similar to the request. The first line is called a status line, and it contains the protocol version, a status code, and a status phrase. Below that, we have header fields like date, the server type, and content type. Then comes another blank line, and finally the entity body. This entity body is where the actual requested HTML file or image actually lives. Now, those status codes found in that first line, that is a guaranteed exam topic. Let's run through them. 200 OK means your request succeeded and everything is good to go. 301 moved permanently means the object relocated and the server is telling your browser where to automatically redirect you. 400 bad request indicates your browser sent a message with a syntax error that the server simply couldn't understand. 404 not found is the famous one. You clicked a dead link and the document is just missing. And 505 HTTP version not supported means the server doesn't support the protocol version your browser is currently trying to use. Section 4, State and HTTP cookies. We established earlier that HTTP is stateless and suffers from amnesia. So let's shift our narrative to how servers successfully overcome that amnesia to remember exactly who we are. They pull this off using cookies. You can think of a cookie as a unique corporate ID badge. There are 4 required components to make this whole thing work. First, the server sends a set cookie header line in its initial HTTP response to you. Second, your browser includes a cookie header line in its next HTTP request to that server. Third, your browser keeps a cookie file saved locally on your own machine. And fourth, the website maintains a back-end database linking that specific cookie ID to your user profile. Now, while this is amazing for user sessions and authorization, it also allows third parties to track your browsing habits, which definitely brings up some major privacy concerns. Let's look at Susan's e-commerce shopping journey to really visualize this theory. Susan visits Amazon for the very first time. Her browser sends a standard HTTP request. Amazon's server creates a unique ID just for her, let's say it's 1678. It creates an entry in its back-end database and replies with an HTTP response containing the header setCookie1678. Susan's browser securely stores this ID. A week later, when Susan comes back to buy something, her browser automatically sends cookie1678 in the new request. The server queries its database, completely remembers who she is, and boom, her shopping cart from last week is perfectly restored. Part 5, Web Caching and HTTP/2. We've covered how connections work. Now let's explore the sophisticated technologies designed to get rid of those 2 RTT delays we calculated earlier. First up is web caching, which is also known as using a proxy server. A web cache dynamically acts as both a client and a server. Your browser is configured to send all of its HTTP requests to this local cache first. If the cache already holds the requested object, it returns it to you immediately without ever bothering the origin server. This drastically reduces response time because the cache is geographically much closer to you, and it massively reduces traffic on an institution's access link. It basically makes the internet feel lightning fast. So, the crucial point is this performance math scenario. Imagine your university has a 1.54 megabits per second access link to the public internet and a lengthy 2-second RTT to an origin server. If thousands of students all attempt to download the exact same lecture slides, that access link will max out at 99% utilization, causing excruciating minutes of delay. However, if we install an institutional cache on the local network, the very first student downloads the file, the cache saves it, and the next 999 students retrieve it instantly over the high-speed local network. We completely bypass that slow 1.54 megabit bottleneck. Finally, let's contrast the evolution of these protocol versions. HTTP/1.1 introduced persistent connections, which was great, but it schedules requests on a strict first-come, first-served basis. This creates a severe traffic jam known as head-of-line blocking. It's like being at the grocery store with one tiny item, stuck in line behind someone with 2 overflowing carts. Imagine a tiny text file stuck waiting behind a massive 1 gigabyte video file on the exact same TCP connection. HTTP/2 was specifically designed to solve this. Its key objective is decreased delay in multi-object requests. It uses advanced pipelining, breaking messages into smaller frames so that small objects are never blocked by larger ones. All right, let's do a high-energy, rapid-fire revision of the absolute essentials you must memorize for your exam. Number 1, HTTP is an application layer protocol that utilizes TCP port 80 and is fundamentally stateless. 2, a URL consists of a hostname and a path name. 3, the exact mathematical formula for non-persistent HTTP response time is 2 RTT plus file transmission time. 4, cookies overcome server amnesia by utilizing 4 distinct components to maintain state. And 5, web caches act as proxy servers to drastically reduce both network traffic and client delay. I'm going to leave you with this classic, provocative Viva question that networking professors absolutely love to ask. If the HTTP protocol is entirely stateless and suffers from complete amnesia, how exactly does an e-commerce site remember what you placed in your shopping cart 3 days ago? Well, if you can confidently walk them through those 4 components of cookies, the set cookie header, and the backend database, you are perfectly prepared to ace this exam. Keep reviewing these foundational concepts, understand how those packets flow, and you're going to do exceptionally well. Thank you so much for joining me on this explainer.